Good morning, everyone. Welcome to Rogue7, Rogue Engineering Station Attacks on S7 Simatic PLCs. We're in Breakers GHI. We're here to listen to Uriel, Malin, and Sara, Bitan. Couple announcemements. Before we begin, stop by the business hall located in Mandalay Bay, Oceansides, and Shoreline ballrooms on level 2. Please also join the Black Hat Arsenal in the business hall on level 2. Last but not least, of course, turn off your phones. And he asked me to announce that they will be having a white paper up on the Black Hat website at some point in the near future. With that, I'll turn it over to them. Enjoy.
Good morning, all. The title of our talk is Rogue7, Rogue Engineering Station Attacks on Simatic S7 PLCs. This is joint work with Professor Eli Biham, Aviad Carmel, and Alon Dankner from the Technion, and Professor Avishai from the Tel Aviv University. Uriel and me will be presenting. My name is Sara. I'm a senior researcher at the Technion Hiroshi Fujiwara Cybersecurity Research Center, and I'm the founder and CEO of Cyclox, Secure System Design and Audit.
My name is Uriel Malin, and I am a master's student at Tel Aviv University, advised by Professor Avishai. I am also a security researcher at Medigate, Healthcare IoT Security.
So we are going to present to you in this talk several design vulnerabilities we've exposed in the Siemens proprietary S7 protocol, and we are going to describe and demonstrate an exploit that performs remote stealth programming on an S7 PLC. Those of you who are familiar with Game of Thrones will in particular enjoy this talk. Others, don't worry. I'm going to introduce you to the three characters that are going to appear in this session. Grey Worm, the man of action, the man in the field, is going to represent the ICS operator. Look, he even wears a helmet, so it's safe for him to walk on the production floor. Tyrion Lannister, the man of brain, design, and vision, will represent the ICS engineer, and Arya Stark, the assassin, the faceless girl, will represent the impersonator, the attacker. So, critical infrastructure system, we become more and more dependent of them in our daily life. Most of these systems, such as electrical grids, water facilities, and transportation systems, are controlled by industrial control systems. These are distributed computerized systems that many times span across dozens or even hundreds of miles. They operate and monitor physical devices. The PLC is the core of the ICS. It is a robust and reliable device designed to work under extreme environment conditions, since many times it is installed outdoors. The PLC is connected to physical devices, such as centrifuge, wind turbines, and generators, and it runs a control program that samples, sensors, and triggers active device according to the results. The PLC constitutes a bridge between the virtual and the physical worlds. This makes it, in particular, interesting for attackers, and it is indeed the target of our attacks. I've described the PLC physical interfaces. It also has multiple virtual interfaces. The control program running in it can expose its variable to an HMI software that the operator can use to monitor and modify value of control variables in the PLC. The engineer, Tyrion Lannister, can use the engineering workstation to write its control program, and he downloads the control program to the PLC through an interface with a software layer that we call the PLC operating system. The interfaces with the HMI and the engineering workstation are most of the time vendors' proprietary. However, the PLC also has standard interfaces, web server, and SNMP server. In the Siemens world, the PLC that we're discussing is the S7 1500. Siemens HMI software is called WinCC. The engineering workstation software is called Step 7, and the proprietary protocol that Siemens uses for communication between the HMI engineering workstation and PLC is called the S7 protocol. Both packages are packaged into a software that's called TIA, and this is the package that we're trying to impersonate. The focus of this talk is on the S7 protocol. This is the protocol that we are trying to exploit. Most of the ICS systems are separated to several physical production floors. The typical structure of a production floor is a layered structure. You see in the lower layer the active devices. The middle layer consists of the PLCs, the control layer, and the upper layer consists most of the time of local HMIs. Several production floors are connected to a main manufacturing zone where the control and the command center is located. They're also located, there are several central application servers and an historian. In the main manufacturing zone, we also see the engineering workstation. In a minute, it will become clear why we've emphasized it. But note for now that it is somewhat isolated from the rest of the servers in the main manufacturing zone. The main manufacturing zone is usually connected to the corporate network that many times has an ERP server in it, and this network many times connected to other external network, sometimes even to the internet. This connection to the rest of the world is the source of troubles and the source of attacks. The most famous attack on ICS is Stuxnet. Anybody heard about it? No. So it was discovered on September 2012, and it targeted the previous version of the Siemens PLC, the S7 300. It infected a DLL that was common both to the HMI and the engineering workstation packages. What Stuxnet, this DLL is the one responsible to communication with the PLC. What Stuxnet did, it replaced the DLL with its own malicious version, practically taking control over the full communication with the PLC, which enabled it to inject control program and do whatever it wants. The protocol that was used by this PLC is a previous version of the S7 protocol. Now, the engineering workstation, on the one hand, if one takes control over it, then it is in complete control of all the PLCs in the ICS. On the other hand, it's a highly sophisticated software package with many features running on general-purpose operating system. This makes it error-prone and vulnerable. And typical ICS attacks exploit vulnerabilities in the engineering workstation, such as the first vulnerability that enabled Stuxnet to replace the DLL with its own malicious DLL, or a vulnerability that was discovered less than a month ago that enables an unauthenticated user to take control over the TIA through its web servers. By now, users realize that the engineering workstation is the soft belly of the ICS. Hence, in most production deployment, users disconnect it from the production network, keep it somewhere safe, and take it out only when needed for troubleshooting or maintenance. Our attack, unlike typical ICS attack, exploit vulnerabilities directly in the PLC, specifically in the PLC operating system in its implementation of the S7 protocol. The implication is that we can use any vulnerable machine or device on the network as an attack machine. Anyone cares to speculate how many ICS deployments contain vulnerable, outdated operating system? All of them, right? Anyone said Windows XP? In most of the ICS deployment I've been to, there's, when you ask, yes, there's some Windows XP in some deserted dark room that runs some application that is not supported on any other operating system. Connect it to the deployment network, and we can use it as an attack machine. So, the victim of our attack is the S7 1500 PLC. It is one of two new members in the Simatic PLC product line. S7 1500 is the high-end PLC. The other member is the S7 1200. Since Stuxnet was discovered, Siemens made significant investment in security enhancement of the Simatic PLCs. They came up with a new version of the S7 protocol, which applies cryptographic integrity protection to the messages. This is the protocol that we discussed. They provided know-how and copy protection to the control program, and they also added a PLC access control mechanism that is based on password. This mechanism can be used to mitigate the download attacks that we're going to demonstrate. However, it is not used by most customers, and we consider it infeasible. It might be feasible for small ICS deployment that has two dozens PLCs, but it's impractical to protect a deployment with hundreds of thousands of PLCs with passwords. The S7 protocol, it was originally running in the OSI communication model, hence it runs on TCP/IP port 102, which is ISO transport over TCP. It is a session-oriented protocol. The session begins with a four-way handshake, during which the parties agree on the integrity protection key that they are going to use, the version of the protocol that they are going to use. We've detected several versions. All our discussion is focused on a version that we call P3. In the second message, the PLC sends a session ID to the client, which is most of the time the engineering workstation. The client must return it in all subsequent messages. Hence, this session ID serves as a cookie. The protocol enables the client to create, modify, and delete objects in the PLC internal memory. Here, for example, we see creation of an object that is called server session in the PLC internal memory. It will be used to hold all the attributes of the session, including the cookie, the integrity protection key, and so forth. The key of the vulnerabilities that we are going to describe is in the S7 P3 handshake protocol. This protocol is based on public key cryptography. The PLC has a private key. The client must have the respective public key. The session is initialized by the client that sends an hello message with some random ID. The PLC generates a challenge, a random challenge, and it sends it to the client together with a session ID that I already say serves as a cookie, and the model and the firmware version of the PLC. These will be used to determine which protocol version to run. The client then generates a random key derivation key and sends it together with additional keys encrypted with the PLC public key. Uriel, in the second part of the talk, will dive into the details of the handshake protocol. For now, in the third message, the client sends the session ID, the keying material encrypted with the PLC public key, and a response that should match to the challenge that the PLC sent. The PLC verifies the response. If everything confirms, it sends an acknowledgement, and both sides derive a symmetric session key, which is a function of the challenge that the PLC generated and the key derivation key that the client generated. Now, in order to analyze the properties of this protocol, I'm going to compare it to the protocol you all know, which is the SSL protocol. So in both protocols, there's only one-way authentication. The PLC is authenticated and the client is not authenticated. Here, the PLC serves as a server. In both protocols, the client generates some random keying material and sends it to the server encrypted with the server's public key. However, there's a huge difference between the SSL protocol and the S7 P3 handshake. And the difference is that in SSL, each server has its unique private public key pair, whereas in the S7 P3 handshake, all PLCs from the same model and the same firmware version share a single private public key pair. The implication is that if we know which public key to use, and if we understand the details of the protocol, then what we have is one ring to rule all the S7 1500 PLCs in the world. But unlike Golem's precious ring that was unique in the world, this ring can have multiple forged copies and all of them work perfectly well. And this is the key to our attacks. So now we're ready to describe our attacks on the P3 program download exchange. First, let me describe to you how does the object that represents the control program look like. So its name, which is not that important, is a program cycle object block. And it has three attributes that I want to point to you. The first attribute is the object code. This is the code actually running in the PLC. The second attribute is the source code that represents the source matching the object code. And the third attribute is an object MAC taken over other attributes of the control program. Now, the whole message that creates the control program object is protected using HMAC SHA-256 with the integrity protection key that was established by the handshake. In our examples, we are going to use two simple programs. The yellow program is an innocent program written by Tyrone, the engineer, which does what it's supposed to do in the ICS. The blue program is a malicious program written by Arya, the attacker. Note that the structure of them is identical. We have the object code, the source code, and the object MAC. Now, our goal is to run the malicious program, the blue malicious program in the PLC, while concealing it from the operator. Clearly, there is difference between these two programs, okay? The yellow program sets LEDs number 0 and 1, while the blue program sets LEDs number 2 and 3. In real lifetime attacks, of course, the difference will not be that apparent. For example, you could have the blue program increase the rotation speed of a centrifuge while manipulating the HMI variables. Clearly, it will not be as noticeable as here. Before going into the attack, flows, let's look at a legal flow of a program download. So Tyrion sits at the engineering workstation and programs the yellow innocent program. He then hits the download button, and the four-way handshake takes place. Integrity session key is established and shared between the engineering workstation and the PLC. At this time, the control program creation message is constructed. It is integrity protected, as indicated by the yellow, by the little red seal, and it is sent to the PLC. When the PLC receives and verifies, it runs the program, the LEDs are set, and the program is running. Siemens also provide the engineers with a program upload feature. We already say that the TIA is disconnected from the network. So if you have to do maintenance or troubleshooting, you come with a TIA that you took out from the cupboard, connect it to the deployment network, and then press the upload button to retrieve the program running in the PLC. Tyrion presses upload again. Handshake takes place, integrity session key, and the source object is retrieved from the PLC internal memory. It is integrity protected and sent over. Of course, this is the right source program, and it is sent to the engineering workstation. Now let's start with the description of the attack finally. So we already said that there's no engineering workstation in the production network. So let's bring it with us. So the attack system that we constructed, we call it Rogue TIA. It consists of a legitimate TIA version 15 and an attack proxy. The attack consists of two phases, a setup phase and an attack phase. Let's describe first the setup phase. So Arya can run the setup phase anywhere in the world, provided that she has an S7 1500 PLC. So here she does it in my lab in the Technion in Haifa. She programmed the blue malicious program. And in this setup phase, the malicious proxy is in tap mode. It only listens. She presses the download button, handshake takes place, integrity session key is created. The control message is integrity protected and delivered to the PLC. The only thing the malicious proxy does is it records the whole flow of the messages into a pickup file and saves it for future use. Now, of course, if you attempt to upload, then you will have the blue program in memory, which is what it's supposed to do. Now to the attack phase. The attack phase happens in the victim premises. Here you see Arya located in King's Landing. This time she brings in the workstation and programs the yellow innocent program. She presses download, again, handshake takes place, integrity session key establish, but since we have the TIA under our control, this is a rogue TIA, so what we do, we share the integrity protection key with the malicious proxy. There are many ways to do it. We chose to do it by extracting the integrity session key from the TIA's memory and sending it over to the malicious proxy. Now the control program message is created. It is integrity protected with the session key, and the malicious proxy intercepted. Our first attempt was to replace the yellow object code with the blue malicious code. When we tried to send it to the PLC, it detected there's something wrong and it rejected it. We highly appreciated it, since it means that Siemens are making some precaution measures. Our second attempt, we substitute also the Mac object to the blue Mac object. we applied integrity protection, since we have the integrity protection key, and we sent it to the PLC. What do you think happened? Well, you should know by now, otherwise we wouldn't be standing here talking to you from this stage. So, we sent it to the PLC, he accepted it. Which program was running? The malicious blue program that set LEDs number 2 and 3. So, Siemens did very well when they added MAC protection to the attributes of the control program. However, for some reason which I cannot understand, they choose to apply it only to the object code and not to the source code. So we have the situation where the blue malicious program is running in the PLC, and when you hit upload, you get the yellow innocent program, since this is the source code. And clearly, they're different. Are we done yet? Almost. TIA is a huge software package. It weighs over 5 gigabytes. So it's impractical to use it as an attack payload and carry it to a production ICS. This is the reason we came up with our Rogue Engineering Station attack. So the Rogue Engineering Station is simply a Python script that impersonates a TIA. It gets as an input the victim PLC IP address and 2 PICA files, yellow and blue, that were prepared during the setup phase. What it does, Arya is again at the victim premises. She chooses the innocent and the malicious program she wants to inject. Then she creates this hybrid program with the malicious object and the yellow source, and she presses download. At this stage, the handshake takes place, and the integrity session key is constructed. Now, unlike the previous attack where we were man in the middle, sort of, here we have to fix all the cookies that the PLC sends to the client. So we fix the session ID, we fix all the other cookies that are planned there, we create integrity protection, send to the PLC, malicious program running, innocent program uploading. Again, we did stealth injection of a control program. So to wrap up this part, if Arya can control the PLC in my lab in the Technion, she can also control the PLC in the gate of the wall to open it, even though she's not Jon Snow. And she can also control the PLC in King Landing's gate, although she's not Cersei Lannister. Now I'll give you Uriel for the fun and the juicy stuff of the reverse engineering.
Thank you, Sara. So I am Uriel Malin, and I will show the P3 handshake details. Then I will give some tips for a better reverse engineering process. And then we will show a very cool demonstration of our attacks. The technical part won't be so long, so brace yourselves. Okay, so recall that the session key is derived by the challenge and by the KDK. So the challenge is sent from the PLC to the client, and the KDK is sent through this encrypted keying material thing to the PLC. But what is this encrypted keying material? So first of all, let's list the cryptographic primitive which in use. So there is public-private key-based asymmetric encryption, which is done with elliptic curve LGAML. There is also symmetric key encryption, which is done with AES in 2 modes, ECB mode and counter mode. There is a key derivation function, KDF, and there is also a non-cryptographic checksum tabulation hash. So, how the TIA share the KDK? Generate 20 bytes pre-key. Encrypt it using elliptic curve LGAML-like encryption with the PLC Public Key and add it to the keying material. Calculate KDF on pre-key and get 3 buffers: the checksum encryption key, the checksum seed, and the key encryption key. Then concatenate the KDK to the challenge that was received from the PLC encrypt them using AES in counter mode with the key encryption key, and add to the keying material. Initiate the tabulation hash with checksum seed and calculate checksum over the AES output. Encrypt it using AES ECB mode with the checksum encryption key and add to the keying material. Now, the TIA can send the keying material to the PLC. When the PLC receives the keying material, the PLC and only the PLC can use its private key to decrypt pre-key and extract the KDK. So now the PLC is able to derive the session key too. The public keys are stored in compressed key files at a TIA installation folder. Each key file contains some metadata like version, key type, key and key family, and also key data, which is the PLC public key for the elliptic curve gamma-like encryption. For example, this is a real censored key file. Its version is 1, its order number is S7 1500 connection, its family type is S7 1500, and the key data is the PLC public key. But if we take a better look, we will see that the film version is empty. Why? The reason is that this PLC public key is good to connect to any S7 1500 PLC. And this is our ring. This is the ring to rule them all. With this public key, we can connect to any S7 1500 PLC. So now that we have found our ring, we could use it with our Rogue engineering station in order to establish the session key. So, first of all, pre-calculate pre-key encryption and checksum encryption key, checksum seed, and key encryption key. This step could be offline in our setup phase in our lab. Then, when the attacker is on the product environment and start the handshake, let Python do the symmetric encryptions and the checksum calculation to build keying material 2 and 3 based on the challenge that was sent from the PLC. Now, our Rogue engineering station can send the keying material to the PLC, and the PLC will extract the KDK and derive the session key. But we need to derive the session key too. So the Python script wraps the session key derivation function from the relevant DLL. We didn't reverse the session key derivation function f due to lack of time, but we know that this function is a static function and it doesn't depend on any external information. Okay, now I'll give some tips about reverse engineering the TIA handshake. So, TIA is huge. First of all, find your target files. In our case, the target file was OMSP core managed DLL. This is the main S7 communication DLL. This is a mixed mode DLL, which means that part of the DLL is written in C# and is compiled to manage CIL bytecode, and the other part of the DLL is written in C++ and compiled to native unmanaged x86 opcodes. Then, choose your tools. When we want to analyze the managed code, we can ignore the native part of the DLL and load the DLL in Reflector or DNSpy and read its code. When we want to analyze the native C++ code, we can ignore the managed part of the DLL, load it in IDA Pro or in Ghidra, and analyze the native code. Then, I recommend to improve your reverse engineering starting point. So, how can we do that? Okay, so tip number 1, identify native code entry points. So this is a snapshot from OMSP core managed DLL, managed part, open in DNSpy. If you look at the bottom of the snapshot, there is a call to a OMS client session set server public key function. Okay, so let's click on this function. Okay, so we barely can see the prototype of S7 server public key. But where is the function body? So dnSpy helped us in parsing the P header file, and it can tell us that this function is an unmanaged function. We open it during the analyzing of the managed part, so clearly we won't see the source code of this function. But how can we find its implementation? So if we take even a closer look, we will see that there is also an RVA here. So what is this RVA? This RVA is the relative virtual address of this function in the native part of the DLL. We can load it in IDA, take the image base, add this RVA, and we will reach this function. Now we know that this function is S7 server public key, and we also know its prototype because we see it in the managed part. Tip number 2, C++ and RTTI. RTTI is runtime type information. This is a very cool feature, an optional feature, that allows C++ programmers to examine object types dynamically. The RTTI information must be inside the binary, and we could use it. So, find RTTI object. This could be done by looking for the string RTTI complete object locator with IDA. And then, after we find an object, we can see the name of the class. Here, there is the OMS parser. The reason that this object is interesting because every virtual table of the classes has a reference to this object. So, locate the relevant virtual table by using the cross-references of this object. After we found the virtual tables, we could rebuild the structure which represents the virtual tables and also changing the name of the address, like this. Then combine them all. Scan the .NET metadata and grab the native entry points. Also, scan your IDB and grab the relevant RTTI data. Use IDA-Python to add this information to your IDB. And then, this ugly function, which I guess that most of you can't understand what it does because of all this dereference, with a very few efforts could transform to such a nicely and readable function. Much better, isn't it? Okay, so now let's see the demonstration. Volume, please.
This is our attack setup. Here you have our victim PLC, the S7 1500. Below you have a screen connected to a Windows workstation. On the left-hand side of the screen, you see 3 Windows CLIs that I'm going to use to run our attack scripts. On the right-hand side of the screen, you see a TIA in a read-only mode that I'm going to use to query the PLC as to the program loaded in it. First, I'm going to run an attack script that stops and starts the PLC. The PLC is currently in run mode, as indicated by the green background, and we have a single LED that is set. I'm going to use the script to send a stop instruction to the PLC. The PLC switched to stop mode, the background color has changed, and the LED is cleared. Now I'm going to send a start instruction to the PLC. The PLC switched to run mode, the background color is green again, and the LED is set. Next, I'm going to run an attack script that downloads a program to the PLC. The program that we're going to use is the yellow program from the examples. The yellow program sets LEDs number 0 and 1, so indeed it is running in the PLC. Now I'm going to use the TIA to query the PLC as to the program loaded in it. The TIA gives a notification that the source of the program loaded in the PLC has changed, which is indeed true, because before we had a program with one LED set, and now we have a program with LEDs number 0 and 1 set, the yellow program. Now we are finally ready to show you our stealth program injection attack. I'm going to run an attack that downloads the blue binary and the yellow source. So the blue binary, LEDs number 2 and 3 are set. We added another LED for your convenience, so it will be easier to distinguish between the yellow program and the blue program. Now I'm going to use the TIA to query the PLC as to the program loaded in it. The yellow source was previously loaded to the PLC, and now I loaded it again. So the source program hasn't changed. So the TIA doesn't send a notification. So we have the blue binary running in the PLC. We have the yellow source loaded to the PLC. So indeed our stealth program injection attack is successful. And even if there is a TIA connected to the production environment, it will not be able to detect our stealth program injection attack.
So, to summarize, we introduced vulnerabilities in the S7 P3 protocol. TIA is not authenticated towards the PLC, and there is a one ring to rule them all, a one PLC public key. We also introduced a Python attack tool that impersonates TIA. Download a recorded program to any S7 1500 PLC. We also introduced a stealth mode injection attack. Thank you very much for listening. Any questions?
Did you contact Siemens, and what was their reaction?
Yes, we did contact Siemens. We found some other vulnerabilities that we didn't describe on this presentation, but they are described in the white paper. So Siemens assigned us a CVE number. But apart from this, the main reaction was use password protection access control to mitigate this attack. Any other questions? Thank you very much.